Hello, welcome back. Today we're going to take a look at area between two curves. This is a topic that's going to look a little familiar to us. Earlier this year, when we found area under a curve, like let's say we have a function f of x, and we wanted to find the area between a and b, we would say, well, we can get the area by looking at the integral f of x dx from a to b. That's what an integral finds for us. Well, today we're going to take that same topic, but now we're going to move between two curves. So let's take a look at the following function. It says, let f and g be two functions on the domain a to b. We want to find the area bounded by f and g over this interval. So here's how we're going to do this. This is a very easy topic to do. If I was to look at the first function, on top we have this function f. On bottom we have this function g of x. We want to find the area shaded in between them. To do this, we're going to introduce a new tool for us. It is called the rectangle of math. Now, this rectangle of math is very vital for us in this entire unit. This comes from Riemann sums. What we're going to do is from the top function to the bottom function, we're going to draw a rectangle. Doesn't have to be a very thick rectangle. Matter of fact, it's really a very skinny rectangle like this. Remember, it's really, oops, there's this little rectangle. Now, what we're going to do is we are going to find the area of this one tiny rectangle. Now, like when we did Riemann sums, the base of the rectangle is really skinny. The base of the rectangle is very skinny. So it's so skinny, in this case right here, since it would intersect the x-axis and it's horizontal, this rectangle right here is called delta x. The height of the rectangle, it's vertical. This represents our change in our y values. Now, what we're going to do is we are going to let delta x go to 0. And when we do that, our new rectangle just becomes this. Delta x going to 0, we call that dx. This is still delta y. We can't let that go to 0 because this height will always remain a certain height, but we can change the width of our rectangle. So to get the change in the y values, we're going to go back to our rectangle up here. We're going to look at the top function and the bottom function. If I want to find the height of this rectangle, I would take the top function, f of x, and just minus the bottom function, g of x. So the height, the delta y, will just be f of x minus g of x. And now to get that area, we're just going to take f of x minus g of x, the height of our rectangle, times the width of our rectangle, which we're saying is dx. So it's literally saying like length times width. The length times the width of our rectangle. And that's only for one skinny rectangle, and then we're going to integrate that from a to b to get all of them. And that's our rule right there. So it looks really complex, but it's really simple to do. For example, let's take a look at the next one. Now over here, notice for the second example, we're in terms of y, f of y and g of y. For this one, we're going to draw a rectangle horizontal. So if we blow up our rectangle over here, same thing, on the vertical part, we still have this delta y. On the horizontal part on the bottom, we still have this delta x. But notice delta y, this is my skinny part. I call this my skinny part. We're just going to let that go to 0. The skinny part go to 0. So my rectangle is really dy delta x. Well, to get the change in x values, we're going to take this right side minus the left side, and that's it. So we're going to take this f of y, which is on the right, minus the left, which was g of y. And now my area will just be this f of y minus g of y times dy, and we evaluate that from a to b, or whatever the range would be in this case. And there we have it. So here's kind of a hint for us. This is the hint that I would like to give my students. In the hint, when you're looking for the length of your rectangle, to get the length of our rectangle, we're always going to take the bigger value or the bigger function minus the smaller function. Whoops, can't spell smaller. Let me rewrite that. Not erasing. There we go. So what do I mean by that? Well, very simple. If we look at the first one, here, the bigger function has the bigger y values, while the smaller function has the lower y values. So if the function we say is in terms of x, if the function's in terms of x, we're looking at a vertical rectangle, and it's always going to be the top function minus the bottom function. If the function's in terms of y, like we have over here, f of y of g of y, notice we took the right minus the left, and we use a horizontal rectangle. So if the function's in terms of y, we're going to use a horizontal rectangle, and we're going to use the right function minus the left. So let's look at an example real quick here. We want to find the area bounded by the parabola 3 minus x squared and the line y equals negative x plus 1. So the first thing we're going to do is we're going to sketch it. Now, it doesn't have to be very accurate, but I know that this is a parabola starting at 3 and it opens down, like so. The line y equals negative x plus 1, I can draw that. There's plus 1, and it's just a line going up like so. We want to find the area bounded by those, and that's just this region in between right here. So I'm going to set up my integral. So the first thing we're going to do is we're going to draw a rectangle on the inside. That's our rectangle of mathematics. I want to see this, okay? Draw your rectangle of mathematics somewhere in there. Now the skinny part this time, notice it's horizontal, so that's our dx. But to get the length of our rectangle, we are going to use, because it's a vertical rectangle, notice we are in terms of x. So therefore, we're going to be using a vertical rectangle. So it's going to be top minus the bottom function. Very easy to do. This never changes. Well, what function's on top? There's my top. It's the parabola, 3 minus x squared, minus which function's on the bottom? Well, that is our line, this negative x plus 1. And I'm going to go ahead and simplify that. This becomes 3 minus 1, so that becomes a, 3 minus 1 is 2 minus x squared plus x. There we go. So to get the area of our one rectangle, we're going to take our length, this 2 minus x squared plus x, and multiply it by our width, which was at dx. And to get the entire area, we're going to integrate it. Now, we still have to find the bounds. So let's go ahead and do that. To get the bounds, we just want to find out where they meet. 3 minus x squared equals negative x plus 1. Solving this one, it's a quadratic, so I'm going to bring over my x squared. I get x squared minus x minus 2 equals 0. And this becomes x, minus 2x plus 1 equals 0. So we get 2 and negative 1. And there we go, from negative 1 to 2. This is going to give us our area. Well, so let's go and get the exact area. Pretty easy to do. Just integrate this one. We get 2x minus x cubed over 3 plus x squared over 2. And we would evaluate that from negative 1 to 2. No fancy stuff. Just get an answer. Plug in the 2. We're going to get 4 minus 8 thirds plus 4 halves, whatever that is. Where there's 2 there. Plug in the negative 1, we get negative 2 plus 1 third, because negative 1 cubed is negative 1, and then this becomes plus 1 half. Don't be fancy, just leave it alone. And there we go. All right, go join us for the next video. We'll take a look at some more examples. I'll see you then. Bye-bye.